let's consider a more challenging problem. Here what we've got is a function called printParty. And what it does is it has two nested for loops, similar to dup1, and each time it executes the inner loop, it prints out hello and computes the sum of 1 plus 1. And what's interesting about the difference between this and what we had before is that I starts at 1 and then progressively doubles until it is greater than n, but otherwise is very similar to dup1. Now it might seem like this is very arbitrary, but it actually matches the pattern of what we'll see in real algorithms later in this class, but this is a very artificial looking function that captures the same math. So your goal is to figure out what is the runtime of this function. In other words, what is the order of growth of the runtime? Some function f of n, which we can say that r of n belongs to big theta of that function. Okay? So give that a shot. And this is actually a pretty challenging problem, so I don't actually expect you to get it right. But if you do, great. But if not, we're actually going to repeat this question 3 times with hints in between. So give it a shot, and then I will start giving you some hints. Okay, so regardless of whether or not you came up with an answer you feel good about, I'm going to start by how I would analyze this. So I'm going to, in this table at the bottom, fill in for every value of n, what is the corresponding c of n, where c is my cost model. What I'm going to do is I'm going to count the number of prints, and to guide my understanding and ability to fill in this table, I've got this diagram in the top left, this little 2D grid. And I find this picture, these 2D grids for nested for loops, to be incredibly useful, by the way. That's like just a generally useful, wonderful idea. So let's start by considering n equals 1. Well, when n is equal to 1, then I is going to start off at 1, j is going to be 0, and that's it. We just get one single print statement. Okay. How about when n is 2? Well, in that case, I is going to take on 2 different values. 1, and then it'll double to reach 2. And when I is 2, j will start off at 0, and then it will go to 1, and so forth. And so we'll end up with a total of 3 print statements. We get I equals 1, j equals 0, I equals 2, j equals 0, and I equals 2, j equals 1. Those are the 3 print statements that occur for n equals 2. Okay, how about n equals 3? Then what? Well, in that case, if you look carefully at this code, we'll see that it actually does the exact same thing as if n is equal to 2. Now, if what I just said doesn't make sense, I encourage you to try it out on paper or even run this code and see what happens. It's really important to understand why n equals 2 and n equals 3 have the same number of print statements and why they do the exact same thing when printParty is called with the values 2 and 3. Okay, so on to number 4, or n equals 4. So in that case, I will actually take on 3 different values, 1, 2, and 4. And when I is 4, j is going to take on the values 0, 1, 2, and 3. So we'll end up with, in total, 7 print statements if you give the number 4 to this function. And it turns out, for similar reasons as before, if we give n equals 5, 6, or 7, we're still going to get 7 prints. Because if n is 6, that doesn't actually change how many different values I takes on. It's never going to be 6. It's going to double right past it and then fail this check. So to test whether or not you're really following the pattern, I encourage you to try and predict what I'm about to say is what's going to go in this box. So it turns out when we get to 8, there's now an additional 7 values that j will take on, 8 values that j will take on when I is 8, for a total of 15. Now when we move up to n equal 9, 10, 11, 12, 13, 14, 15, all of those will still print 15 times. And then naturally, if you're following the pattern here, when we get to 16, we'll end up with 31 print statements and so forth. So summarizing what we've seen so far, the count of the number of print statements is equal to 1 plus 2 plus 4 plus ... plus n. And that applies as long as n is a power of 2. So for example, if n is 8, it's 1 plus 2 plus 4 plus 8. If n is 16, it's 1 plus 2 plus 4 plus 8 plus 16. And that's what we've got here. So given what we've just observed, either looking at this table or trying to imagine solving this sum in your head, try and figure out what is the runtime in big theta notation. Okay, again, regardless of whether or not you have an answer you're happy with, I'm now going to give you a third hint. So I'm just going to make the interesting observation that if we expand our table, so before we went up to n equals 18, now I'm going up to 715. So we can see that the counts of the number of prints continually increases, so that by the time we get to 715, it's 1023 print statements. If I compare that to, say, half n and 2n, just arbitrarily, we'll see that, well, the number of prints actually always seems to lie between half n and 2n. So for example, if n is 185, half n is 92.5, and 2n is 370, and the count lies between them. I think that's an interesting fact. So given that hint, what do you think the runtime might be? Okay, so in this case, I'm now going to finally tell you the answer, which is n. And so there's two ways to think about this. One is, well, let's just plot half n and 2n and our counts. And what we see is that while the counts do jump in this discrete manner suddenly at each of these powers of 2, overall it's bounded above by 2n and below by half n for very large n, and therefore it is linear by the definition of big theta. Now, an alternate approach is to compute the exact solution for n's that are powers of 2. And we could say, for example, that 1 plus 2 plus 4 plus ... plus n. If thinking carefully about this, you can derive that the result is 2n minus 1, work not shown. But as an example, to show you that this is so for n equals 8, if we look at the left-hand side here, LHS is left-hand side, then 1 plus 2 plus 4 plus 8 is 15, and the right-hand side is 2 times 8 minus 1. So that's another approach. And of course, the order of growth of the function 2n minus 1 is, of course, n.